Hello, everyone. Mr. Minnick is my name. Glax Firestorm is my pseudonym. Math is my game. Bad math jokes is not so much my game. Today I'm joined by a class that I inadvertently said that they think I'm a bad guy for giving them quizzes, and they don't think I'm a bad guy. But anyway, they're excited to be here today. So I'd like to give them a shout out for bringing their A game and being ready. So here we are, Algebra II, Chapter 6, Section 7, Inverse Things. It's relations and functions. There's a reason the word relations shows up, which hopefully you'll see in a minute. So I'd like to start off by looking at these two functions. Example 1, let's look at y equals the square root of x plus 1. Notice where that plus 1 is. That plus 1 is under the square root. Everybody see that? Okay, good. And then we'll graph another function. I'm going to use y again. Y equals x squared and then minus 1. So you might observe that the minus 1 is not inside a quantity with the x being squared. We're going to talk about how to calculate, how to compute, how to find an inverse given another function. So what I'd like to show you on a graph is what the graphs of these two things looks like. And I haven't got my TI Inspire hooked up yet, so maybe we'll just kick it old school for a minute. So if we try to graph this red one, we're not going to graph this until the end of the chapter, which is kind of unfortunate. But anyway, nonetheless, if I just graph the square root function, it goes through the origin, it goes through 1, 1, it goes through 4, 2, and it goes through 9, 3. But I'm not graphing the square root function. I'm graphing the square root function. What's that plus 1 do to it? Moves it to the left. We brought our A game today. Awesome. You guys are great. Thank you for making my day better so far. So this new smartboard, I don't think it's gonna cooperate here. Let's see, grouping. Really? Grouping. There we go. Group. Let's try that again. Grouping. Group. Got a new computer, new smartboard software, new sound software. We'll see what happens. So that's what the red one looks like. So with respect to the coordinate plane, I'm going to label some points that this goes through. Okay, this is real important. There's a big idea right here. So we got the point -1, 0. We've got the point 0, 1. We've got the point 3, 2. And we've got the point 8, 3. So those are some points that the red function goes through. Everybody see that? Okay. Now I'm going to graph another line. Maybe you can tell me what line this is. Maybe you can't. You should be able to. Anybody remember the equation of that line? Y equals x. Good. All right. So now it's time to graph the green function. What I'd like to do with the green function is something we've never, ever done in this class. I'm going to restrict the domain of this. I'm going to say for x greater than or equal to 0. So what I want to do is I don't want to graph the whole thing. I just want to graph a restricted version of it. It's kind of like NASCAR. You know how to confuse a NASCAR driver, right? You gotta make a right turn in front of them. But anyway, NASCAR drivers, they only turn left unless they're on a road course, and I think that's kind of cool. But they run restrictor plate races, right? Where they don't get the full horsepower of the car. Well, we're running a restriction. So the deal is, we're saying because of this, we're not going to graph an entire parabola. Does that make sense? Okay. So x squared minus 1 is translated down. It goes over 1 and up 1, and over 2 and up 1, 2, 3, 4 and over 3 and up. There's 4, 5, 6, 7, 8, 9. So the graph of the right-hand side of it looks like that, and that's all the more I'm going to graph. And you might ask yourself, why on earth didn't Mr. Minnick graph the left side? Well, because if I graphed the left side, if I graphed the left side, I would be violating the restriction on the domain. Do you see what I got going on there? Now, the interesting thing, the fascinating thing, is that your TI graphing calculators are capable of restricting the domain of a graph. And I really wish I had the TI Inspire software installed on this new computer, but I don't. So I'd like to go ahead and graph this on my 83 for a minute. I told you we're going to kick it old school today. So I'm going to reset this calculator. So I'm graphing the square root of x plus 1. I'm graphing x, and I'm graphing x squared minus 1. Now here's where the magic happens. I'm pretty sure the notation is I have to put a comma in here. I hope I get this right. And then, oh no, maybe I forget how to do it on this calculator. Oh, no, I don't put a comma in. I have to hit divide. It's really weird. Why I hit divide, I have no idea. And then in these grouping symbols, I'm going to put x is greater than, bless you, or equal to 0. And I think that'll do it. Yeah. So we saw a TI 83 for $50. That's a good price. The 83s are a good calculator. I've got a whole host of games for these. I've got Pac-Man, I've got Tetris, I've got Doom, I've got Fruit Ninja, I've got Doom, I've got Yahtzee, Super Mario. Dig Dug, I'll have to look on ticalc.org and see if it's there. If there's time at the end of class, maybe I'll check that out. Dig Dug is cool. All right. So the green function, if I look at some points that the green function passes through, the first one I see is 0, -1. And the next one I see is 1, 0. And the next one I see is 2, 3. And the next one I see is 3, 8. Interesting. Anybody see what happened? They're reversed. They're flipped. X becomes Y and Y becomes X. Who can tell me something art related with respect to this line? How does the green function and the red function compare with respect to the line? What do we got? They're symmetrical with respect to that line. There's another word I'm looking for, yeah. They're reflections across, around, or about that line. So let's jot a few of these things down. Inverses. Inverses. And when I say inverses, I'm talking about inverse functions and or relations. So inverses, a couple properties about them. If we think about the graphs, they are reflections. They are reflections about the line, y equals x. In this context, the word about doesn't mean pertaining to, it means across, around, on the other side of. So, as was mentioned, they are symmetric with respect to that line as well. I'm going to give a shout out to Liz Hilverding. She noted that at some point, if the function or graph ever crosses the line, they'll cross in the same point. They'll cross in the same spot. So, kind of a cool observation. So we also noted that x becomes y, and y becomes x. So if we compare a function to its inverse, or a relation to its inverse, the x and y values of one become the y and x values of the other. Hey, wait a minute. Aren't x and y like the domain and range? So because of that, what ends up happening is the domain of some function f becomes the range of its inverse. And notationally, this is the first time I'll use this inverse notation. Those of you who remember from geometry about inverse sine, the notation we use is an exponent of negative 1. So notationally speaking, that means inverse. And this is, I'll be honest with you, this is one of those things in math, one of many things in math that can confuse some people. Because what does an exponent of negative 1 tell you in a chapter ago, a couple chapters ago? It's a power, and what does a negative exponent do to something? In case you don't know, I'm flipping the desk over. It flips it over, or puts it under 1, right? So it doesn't mean, to be clear, we're not talking about 1 over f. It doesn't mean 1 over f in this context. That negative 1 exponent just simply means the inverse of the function f. Does that make a little bit of sense? Yeah, I flipped over a desk. That's what all the commotion is. There's a desk now sitting upside down in the first row. Yeah, question. There's a question about, does my projector have a camera on it? No. I'm going to put a room mic in. Yeah. The new laptop has a mic built into it, so we'll see what we can do. We'll see what we can do. Cool. So, because of this statement, we could also go on to say that the range of f becomes the domain of y, or of f inverse, right? So, and I'll just say and the other way, and the other one, and the other one. So when I say in the other one, I mean the range of f is going to become the domain of f inverse. So we'll go back to that last graph and we'll check that out. We'll go back to that last graph and we'll check it out. Because there is a little caveat to it. So if we look at the red function, its domain, goes from what to what? What's the domain of that red function? Thank you. Negative 1 to infinity. And negative 1 is actually included. Now let's go ahead and look at the green function, and let's look at the green function's range. All the y values that are possible for that green function. What's its range? Negative 1 to infinity. Surprise, surprise, surprise. Imagine that. So we got a domain here, range here, el mismo. Is this stuff making sense so far? Good. You know, it's kind of sad that I normally don't get too upset about actors and actresses leaving the earth, passing, expiring, cashing in their golden chips. But, you know, a couple of weeks ago, Roscoe P. Coltrane passed away. The guy that played Roscoe P. Coltrane from the Dukes of Hazzard. Anyway. Cooch. All right. The range of the red function goes for... Anybody know what the range of the red function is? It goes from what to what? 0, and it doesn't look like it gets that far up, but it will. It just takes a while to get there, but it does. It goes all the way up to infinity, if you can believe that. And we do include 0. So guess what the domain of the green function is? 0 to infinity. All the x values of that one are 0 to infinity. And again, surprise, surprise, surprise. So how do we feel about making the connection from function to its inverse, to the domain, the range, the x and the y, the reflection? Is that all copacetic? Do we feel pretty good about that? Okay. All right. So the other big idea then, aside from seeing this graphically, is being able to compute one, being able to calculate one, being able to find one. So I'll offer 2 algorithms, and I'll let you be the judge which one you like better. One is called the list method. Sometimes I call the list method reverse and undo. Reverse and undo. So what you do in this particular method is you make a list you make a list of operations on X. And it's kind of tough to make the list if I'm being completely forthright. And I should probably clarify this. I should make it a little bit stronger than saying make a list. I should say make an ordered list. Make an ordered list of the operations on X. What happened to X? Here's where the reverse and undoing comes into play. You're going to make a new list. And while you're making that new list, what you're going to do is you're going to reverse the order. You're going to reverse the order. And you're going to undo the operation. And undo the operation. So what operation undoes adding? Subtracting. What operation undoes multiplying? Dividing. What operation undoes cube rooting? What undoes cube rooting is cubing something. So a couple little things words of caution on this. Do each successive step to the quantity that's there. So whenever you go to do that next operation, you're going to have to do that operation on whatever quantity it is you're working with. You'll see what I mean in a minute. So that's this method that I like to call the reverse and undo method. You make an ordered list of operations that happened to X. You make a list, a new list, and reverse the order and undo the operation to each successive step to the quantity. This doesn't make any sense unless we look at an example, does it? So let's look at an example. Not yet? Stand by. Shout out to Carter Chapman for saying stand by. I think Mr. Bartz deserves a shout out though, because isn't that a Mr. Bartz thing? Stand by. All right. Here we go. Example 2. Suppose f of x equals the third root of 2x minus 1 plus 5. Ooh. Should we put this all over something just to make it a little more interesting? We're going to. Let's put this all over 7. I love this list method. It's so cool. It's almost like that guy. Did you hear about the guy the hipster who burned his mouth drinking coffee because he drank coffee before coffee was cool? That was so bad. So here's my first list. Here we go. My first list, what is it that happened to X in the beginning of whatever's going on in this? So I don't know where my magic marker is. Here it is. The first thing that happened to X there. It says 2x. So what happened to X? It was being multiplied by 2 or doubled. So the first thing that happened to X is that it was doubled. Interesting. The second thing that happened to X then, if we can look here, and it's hard to tell where to look, but if we look there, what's the next thing that happened to X? We subtracted 1. Are we starting to get the hang of how to tell what happens next then? Okay, so what's the third thing then that happened to the X or that quantity? We took its cubed root. And then what's the next thing that happened? Either we added 5 or we divided by 7. Added 5, and then finally, we divided by 7. Question. Does PEMDAS apply to that? It sure does. It sure does. Nice. Good call. Yeah. So if you're having trouble with determining the list stuff, think of PEMDAS. Good. So that's our first list. Now this says, let's make a new list. The new list, we're going to put the last first and the first last. I've heard that before, but that's another story. So anyway, the fifth thing is going to be the first thing in this new list. So how do I undo dividing by 7? Multiply by 7. So the first thing I'm going to do in this new list is multiply by 7. The fourth thing is going to become, or the next to last is going to become the next, or the second. So then what am I going to do? Subtract 5. We get the idea now, right? So then what am I going to do? I'm going to cube, right? And then what? Add 1. And then so the first will be the last. And so what's that? I'm going to divide by 2. So now what we've got to do is actually perform those operations to x. Notationally speaking, does anybody recall how I'm going to annotate the inverse of the function f? I'm going to use that little -1 exponent, right? So here's my answer. Here is my ANS, my answer. F inverse of x equals. Now remember, when I do these operations, I got to do these operations to the quantity that's there. So I multiply x by 7, so there's 7x. And then what? Minus 5. Now when I cube, do I cube just the x, just the 7x, or that whole quantity? I cube the whole quantity that's there, so I cube all that. I add 1 to that whole quantity, and then I divide that whole thing by 2. Now if we did this right, remember what our graphs ought to look like, right? And I'll be frank with you, even though my name is not Frank, it's probably a good thing that the TI Inspire isn't hooked up yet, because the TI Inspire doesn't graph cube root functions very well. In fact, it does a horrible job of graphing them. So my numerator is the third root, and this is the original function, by the way, of 2x minus 1, close that, plus 5, that's all my numerator, and that's all divided by 7. So that's my original function. I'm going to graph x, and I'm going to graph what I believe the inverse to be. So I'm going to start up the numerator. I'm going to start up a quantity of 7. X, take away 5, close it. Cube that, plus 1, and the numerator. Divide all that by 2, and I'm going to do a zoom square. Here we go. Let's see how we did. So here comes the original function. Da-da-da. There's the next one. And there's the next one. So let's see how we did. Let me try zooming in a little bit now. So here's the original function. It kind of looks like a snake, doesn't it? Cobra Kai. How'd we do? So let's go to the table and let's see. Let's see if we're all right with the table. The bad thing is we don't really have nice integer points that we're working with, do we? But this is kind of interesting. Well, yeah, no, I guess it's going to be kind of hard to tell with the table. But if we look at the graph, I think we get an idea. We did it right? Good. Hopefully that suffices for everybody. All right. So I said I would offer up two procedures, 2 algorithms. You ready for the next one? The next one is called this. I call it the switcheroo. If I was trying to, I guess I would be a poet, and I don't know it because it's the reverse and undo or the switcheroo. So we replace x with y, and the other way, and y with x. And then we merely solve for y. This is so cool. You're going to love this. You're going to love this. Some people are really good at solving equations. Other people, not so much. We'll see which one you like here in a minute. So we're going to do example 2 otra vez. Example 2, again, y equals, what was it? The third root of 2x minus 1 plus 5 divided by 7. All right. So we're going to replace x with y and y with x. So that's going to look like this. X equals the third root of 2y minus 1 plus 5 divided by 7. So far, so good? Okay. So keep in mind here that we're trying to get this y all by itself. Well, to get that y all by itself, we're going to have to get 2y by itself. So we've got to get 2y minus 1 by itself. So we got to get this third root quantity by itself. So we got to get this by itself. So what's the first thing we're going to have to do? Okay. so we're multiplying by 7. So the first thing we're doing here is multiplying by 7. So that's going to leave 7x is the third root of 2y minus 1 plus 5. So what are we going to do next? Subtract 5. So the second thing we're going to do is subtract 5. Okay. So we're going to have 7x minus 5 is the third root of 2y minus 1. What are we going to do next? We're going to cube both sides. So the next thing we're going to do is cube both things. All right? Are we? There's a surprise. You'll see. If you haven't figured it out yet, there's a surprise. So we get 7x minus 5, the quantity cubed equals 2y minus 1. So what are we going to do next? Add 1. So we get 7x minus 5, the quantity cubed equals 2y. So the next thing we had done, the fourth thing we had done, was added 1. Oh, thank you. Good looking out. I forgot to add the 1 over there. Good looking out. Appreciate that. Shout out to, can I give you a shout out? Shout out to John Laurenchak. Brought his A game today. A lot of you guys brought your A game. Nice job so far. So, and this was 2y, right? So what's the last thing we got to do? Divide by 2. So we divide all that by 2. So here's the only trick to this one. In the end, instead of writing y equals, you know what kind of notation we got to use, right? F inverse or y inverse. So we got to use the inverse notation. Whether it's the bad thing about this method is you have to use y, because if you use f, it kind of gets, almost said effed up, but it gets messed up if you do that. Okay. So anyway, our final answer then will be y inverse equals whatever all this is. So what is that? It's 7x minus 5, the quantity cubed, plus 1 all over 2. And the last thing we had done there, is divided by 2. Let's look at this split screen. do you see it's the exact same thing. We just did the exact same thing. You think the first way, the list way was simpler? Some people might. You're doing the same thing. No matter how you get there, you're doing the same. It's like going to the Eastwood Mall. I was actually by the Eastwood Mall last night, actually. So are there any questions, comments, concerns, short debates, long debates about finding an inverse given a function? Real quickly, and it's really sad that I'm almost out of time for this. Here's the definition of an inverse. F and F inverse are inverses if with two F's. Who knows what that means? If with two F's. I didn't misspell it. No need to neck myself. It's bad for their cerebral cortex. So if with two F's means if and only if. Remember that? It's a biconditional statement. So in other words, if the hypothesis is true, then the conclusion is true. And also if the conclusion is true, then the hypothesis is true. Remember those from geometry? The logic statements? Okay, so F of F inverse of X equals X, and F inverse of F of X equals X. So if you are ever asked to algebraically confirm that two things are inverses, I don't expect you to go through the algorithm. I don't expect you to do the switcheroo method. I don't expect you to do the reverse and undo method. The expectation is this, that you'll find F of F inverse of X and show that that equals X. And you'll also have to show that F inverse of F of X equals X. That's going to be on the test. That's going to be on the homework. It's a big idea. For sake of time, I don't think we're going to run through one of those right now. But this is what it takes to show that two functions are inverses. That's the definition of inverses. I'll leave that up there for a minute. So if F of F inverse of X equals X and F inverse of F of X equals X, then we can say with beyond the shadow of a doubt that those two things are inverses. If they're inverses, then F of F inverse of X equals X, and F inverse of F of X will equal X. So down here, in case you're not sure what all this is about, this is what we did yesterday. These are the composition of functions, right? It's the composite functions. Composite functions. Okay. Oh, there we go. Composite functions. That's what those are. Whew. Well, how do we feel about these inverses? Kind of got a little bit of an idea of where to go with them? One last quick piece of information. Last example. Here it is. Suppose F and G are inverses. Find F of G of negative 6,071. This is kind of like who was buried in Grant's tomb. If they're inverses, we know that F of G of X equals X, right? Well, they're telling us they're inverses. So in this case, then, F of G of negative 6,071 is going to equal negative 6,071. Ha! Got him? I hope so, because there's going to be a question like that on the exercises, and guess what? People are like, well, I didn't know how to do this one. Well, you didn't have to do any work. It's just going to be whatever you're taking G of F of or whatever. So that's it. Does anybody want to give any shout-outs to any of the other classes? No? 5B gets a shout? Well, 5B's not even going to watch this. Any other shout-outs? To who? Beats by Dre. The future Mr. Minnick. Thank you. Appreciate that. Have a nice day. See you next time. Good.